I'm Ben Haskett with Garber Incorporated. Thanks for attending this presentation on fruit and vegetable losses. Imagine, you own a grocery store, and you're having problems with your produce department. You're being forced to throw out fruits and vegetables before they're sold because they're spoiling or going moldy. How can you reduce the amount of produce wasted due to spoilage? We at Garber Incorporated have chosen to investigate this issue.
To introduce our problem statement, 58% of Canada's 61 million tons of total food input is either lost or wasted. Furthermore, Canadian retailers contribute a combined 1.34 million tons of waste, which is almost always avoidable. In terms of food groups, fruit and vegetable waste is amongst the highest avoidable waste contributor from Canadian retailers, where annual estimates reach $4.65 billion. This results in numerous social, environmental, and economic implications, including food insecurity, unnecessary use of resources, and increased costs for the end consumer. The social implications can be difficult to swallow when considering that an average of 840,000 Canadians rely on food bank donations each month, and approximately 10.3% of households with children experience food insecurity. As for the environmental implications, which extend globally, total food loss and waste represent 35.5 million tons of unnecessary surface and groundwater usage and 56.6 million tons of carbon dioxide equivalent emissions. The economic implications of producing 61 million tons of food that never reaches the table was approximately equivalent to 3% of Canada's total GDP in 2016. Furthermore, this dollar amount does not consider utility, equipment, or labor costs, which are imaginably hard to quantify. Approaching this problem required an understanding and view of food loss and waste from 4 different lenses. First, the food supply chain consists of 5 stages. Stages 1 to 3, production to manufacturing, proved to be a challenge because a lot of waste is contributed to bad forecasting practices and demands set out by retailers. Stage 5, consumption, is a challenge because at the individual level, losses are difficult to quantify. Focusing on retail, in our case Zehrs, made sense because Zehrs has made a public commitment to reduce their waste by 50% by the year 2025. Therefore, pushback for implementing change should be minimal. Second, food waste versus food loss, where the latter refers to losses at stages 1, 2, and 3, and the former referring to losses post-production. Third, of the main food groups, we chose to focus on fruit and vegetable waste because most of the waste happening at retail is related to this category and provides a greater opportunity for overall waste reduction. And fourth, avoidable versus unavoidable waste. Unavoidable waste refers to food that cannot be consumed or sold, for example, peelings, bones, and corn husks. Avoidable waste, however, is food that is either expired, damaged, or moldy. In summary, we collectively determined that our highest percentage of successfully reducing waste would result from focusing on avoidable fruit and vegetable waste at the retail stage of the food supply chain.
Our design process was guided by many constraints and criteria. Here we will discuss those that had the greatest influence on our design. In line with our project's goal, the implemented design solution must reduce food waste. Our solution must be food safe, cost less than $70,000 per store, and be compatible with stores' current procedures. We will incorporate design features which minimize the costs, physical footprint, and energy requirements of the solution. In addition, employees will be able to correctly use the design after minimal training. These constraints and criteria had the largest impact on our design process. For a comprehensive list, please see the appendix. We have 2 strategies to reduce food waste: prevention and end-of-pipe. End-of-pipe treatments occur at the end of a process stream and handle waste which has already been generated. In the food pathway, these treatments include waste diversion, such as using food scraps as animal feed, and waste reuse, such as composting. Prevention treatments occur during a process stream and, as the name suggests, they prevent waste generation. In the food pathway, these treatments include improved packaging, altering the food product's enzymatic activity, and improving storage conditions in order to extend shelf life. In this diagram, source reduction, the only listed prevention treatment, is the most preferred strategy for reducing food waste. This is the strategy we focused on. We considered 2 options for preventing avoidable food waste: modified display cases and spoilage prevention treatment. Our interviewees indicated that grocery stores' display cases are already as efficient and user-friendly as possible. For example, the display case for loose peppers, lettuce, and other mistables is shaped to maximize customers' view of and access to available produce, while minimizing the loss of refrigerated air. Since modifying produce display cases was unnecessary, we chose to design a treatment which will decrease produce spoilage. We call this the spoilage prevention treatment. Jacob will give us a tour.
This brings us to a proposed design. Here is a SolidWorks model of our design. This was used to verify fabrication costs based on the material used, as well as dimensioning to ensure the design will fit in the back of stores. The final dimensions are 4 meters long by 1 meter wide by 2 meters tall, with the conveyor belt being 1 meter from the ground. This will allow for comfortable loading and unloading by the employees. The spoilage prevention treatment is split into 3 main processes. Once the produce is prepared on the conveyor belt, it can be brought through the first process, which is fumigation. This uses 5% acetic acid, which is vaporized, in order to disinfect the produce of any mold spores. It will then run through a transitionary rinsing stage in order to remove any residual acetic acid before entering the second chamber. In this chamber, we will have surface water removal. This will only be required for specific produce. For example, leafy greens will be able to omit this process because their display cases have misting stations within them. The treatment process, as mentioned before, is made possible by 5 main design components. First is the conveyor belts. We will be using 2 conveyor belts. One is the inlet and one is the outlet. The inlet draws the produce into the fumigation chamber, while the second is used to pull the produce through the surface water removal chamber. Next is the fumigation chamber, which again uses acetic acid vaporized by a combination of a high-speed pump and 2 atomizing nozzles. The produce will stay here for 30 minutes to disinfect. The rinsing uses potable water and a pump that supplies the water through a deluge or shower-type nozzle system in order to rinse. Lastly is the surface water removal chamber, which is run off of 2 855 cubic feet per minute blowers and will run for 4 minutes. All of the pumps and motors and fans are controlled by the PLC, or Programmable Logic Controller. This can also allow for different cycles. For example, a leafy green cycle can again omit the surface water removal stage, or applying different load sizes will alter how much the fans need to run or how much water is required to rinse, much like that of a regular washing machine.
The top priorities for the final design were safety and ease of use. Fumigation at room temperature allows for minimal energy consumption and doesn't damage the produce in the process. The conveyor is positioned at waist height for easy loading and unloading, and all casing and siding is made of food-grade stainless steel for enhanced food safety. The conveyor belt is made of PTFE, and water connections for rinsing must be connected to potable water supplies. Nebulizing spray nozzles allow for rapid equilibration of the acetic acid, reducing the required treatment time. Vinegar with 5% acetic acid was selected as the primary solution to ensure the safety of the user. Since commercial vinegar is typically stocked in most grocery stores, it is readily available as well as inexpensive, costing around 50 cents per liter of solution. Alternative solutions, such as ethanol or chlorine, were either too expensive or represented greater workplace hazards. Vinegar is effective at killing many mold spores, such as B. cinerea and A. alternata, which cause gray mold and leaf spots. This treatment process will reduce mold spores, reducing allergens present in homes and grocery stores. Stores can also decrease the surplus that they order, which will reduce the overall cost of produce. The reduction in spoilage creates an increased food supply capacity for growing populations or areas with insufficient supplies of produce. Less produce spoilage means less produce to fertilize and transport, which will decrease greenhouse gases from transportation and fertilizer use, and will also lower nutrient loading in rivers and lakes. This reduction of spoilage will also cut down on the amount of produce going to landfills. This process may require longer fumigation times based on the degree of contamination on the produce and may not be effective against all strains of mold. Additionally, the process is subject to user error and may be less effective for heavily packaged or clamshelled products.
Now I'm sure you're all wondering how much this is going to cost. In the interim report, we selected a budget of $70,000 to work with based off a percentage of the store's earnings. As you can see on the slide, the initial costs of the machine are around $45,000. Considering the annual operation costs, the project could run for over 3 years before exceeding the initial budget. As you can see, the acetic acid is the main driver for the operating costs of the machine. This cost was calculated with a typical retail price of 5% acetic acid, meaning there is potential to cut costs further given a bulk discount or industrial supply. We've talked about what the machine is going to cost, but what about how much it can save? It's estimated that $2.25 million is spent per store on produce that is lost. If even 25% of those losses were instead successful sales, then the savings would offset the cost of fabricating, installing, and operating the machine several times over. As we come to the end of the report, I'd like to address our next steps. In the coming weeks, we will be completing our final design report, which will tie together all of the documents we've produced into one cohesive design report. I'd like to thank all my fellow presenters and the audience for coming to this presentation on fruit and vegetable waste from Garber Incorporated.